Hello guys, so welcome again to another video. In this video, we're gonna explore more or in details the flag register because it's very important and we're gonna use it a lot in our assembly language. So this is the flag register. So as you see here, there are many versions of that flag or that register. Basically, you have the 16-bit, then you have the extended flag, 32-bit, and you have even the 64-bit. In our course, we're gonna concentrate on the gray, part here of the flag register, which is 16-bit. Although it's 16-bit, some of them are not used. Some of them are just undefined. I mean, Intel itself doesn't define function for these bits. And some other bits are reserved for Intel. They have their use for that, but they didn't reveal such uses. And many assembly language instructions change the flag register. So, but some of them doesn't change. So not all of them change, but some of them, especially the arithmetic operations and logic operations, it changes them. Some instructions as well act differently based on the flag register. So for example, you have one instruction that has two usages or two functions. It can do both. And we differentiate, or we tell the processor to do one job of, for example, based on some bits in the flag register. So instructions act differently, basically, based on the flag register values. So let's see, what is this flag register from inside. These are the 16-bit from bit 0 here until bit 15. These are 16 bits. The ones that, or the bits that we are usually use when we do arithmetic or logic operations are those marked in this screen, which is the sign flag, SF, the zero flag, the auxiliary carry flag, parity flag, carry flag, and overflow flag. R for reserved. So Intel has some usages for these, or maybe they reserve it for future extensions of their processors. Undefined means they have no function, which is this use here. And there are also other flags, which is the green ones here, which are basically control flags. So you remember, guys, I said in our first slide that some instructions act differently based on some bits in the flag register. These are the bits that I'm talking about. Okay, direction flag, interrupt flag, and trap flag. We're gonna, discuss those in the future. So let's delve into the ones that were in red, which is basically we use a lot with arithmetic and logic operations. Number one is the carry flag. Carry flag is set to 1. I mean, this bit here, let's go back. This bit here will be 1. Okay? Under certain circumstances. Basically, if you have a carry from bit number 7 or the 8th bit, if there is a carry output of that. If you are doing 8-bit operation, if you are doing 16-bit operation with 16-bit register, then if you have a carry after bit number 15 or the 16th bit, then this bit will be 1. Otherwise, it will be 0. And don't worry if you didn't understand my wording or my English here, because we're gonna take many examples and we're gonna see this practically, how it's changing. The parity flag, it's an even parity. And it always checks the low order byte with the low order 8 bits. So if you have operation, this operation 8 bits or 16-bit or 32, whatever, we always check the low order, or the least significant 8 bits. If the number of ones there is even, then this flag will be 0, the parity flag. I'm sorry, it will be 1. Otherwise, it will be 0. Cleared means 0 here. So for example, if you have operation, this operation, has this result, We count here the number of ones. Here the number of ones is 5. Then the parity flag will be 0. If the operation will be like was like this, 4 zeros and 4 ones, here the number of ones is 4, and then the parity flag will be 1. The auxiliary carry flag, it's a carry, but it's you know it do the carry or the flag the carry from D3 to D4. I mean, if you have a carry after the 4th bit or bit number 3 of the operation, then this bit will be 1. We're gonna see examples also, so don't worry if we didn't understand well. 0 flag, this is really easy. If you have a result that is all 0, like for example 8-bit operation and all the output is 0, then the 0 flag here will be 1. So 0 flag equal to 1 when there is a 0. Okay, otherwise it will be 0, means there is no 0. The sign flag, again, it's you know, it relates to the sign of the output. So if there is an 8-bit operation, you know, like this, for example, this bit here will make the sign flag equal to 0. If this bit was 1, like something like this, then SF will be 1. If you have 16-bit operation, then we will look at bit number 15 or the 16th bit. The overflow flag means or will indicate an overflow. Overflow means that you did some operation and the output or the result of this operation, for example, is 9 bits while you are doing 8-bit operation. So 9 bits means you need another bit. So you have overflow here. So at that time, the overflow flag will be 1, means there is some error here that you have, because the error here means you haven't had sufficient, you know, number of bits for your operation. Okay, let's see examples. So here is example number 1. We are adding here 38 hexadecimal to 2F hexadecimal. 38 is just 3 and 8 here, and 2F is 2 and F here. So let's do the, you know, let's clear first. Let's do the addition, because this is an add operation. 0 and 1 is 0 plus 1 is 1. 0 plus 1 is 1. 0 plus 1 is 1. 1 plus 1 is 0, and we have a carry of 1. So basically, this is bit number 3. So the auxiliary flag should be 1. Let's check. Yes, the auxiliary flag is 1, because bit number 3, when we do the operation on bit number 3, we have a carry here. Okay, let's continue. 1 plus 1 is 0, and we have a carry of 1. 1 plus 1 plus 1 is 3. 3 means we have 1 and a carry of 1. 1 plus 0 is 1. 1 plus 0 is 1. Then plus 0 plus 0 is 0. So the sign flag here is 0. Let's check the sign flag. Yes, it's 0. That's good. The output is not 0. Is not 0. So the 0 flag should be 0. That's also right. The parity, we count the number of ones in the 8 bits. We have here 8 bits. Let's count the number of ones. 1, 2, 3, 4, 5 ones. So the parity flag should be 0. Let's check. Yeah, that's right. And we have no carry from the 8-bit. So the 8-bit was 0 plus 0 is 0. So the carry flag should be 0. Good. Let's take another example. We're adding here 9C to 64. Let's check. 0 plus 0 is 0. 0 plus 0 is 0. 1 plus 1 is 2, or 0 is 2 is like this. So 0. So we have 0 and we have a carry of 1. 1 plus 1 is 2 again, which is 0, and we have a carry of 1. So from the 3rd bit, we have a carry. So the auxiliary flag is 1. Let's check that. Yes, it's 1. 1 plus 1 is 0, and we have a carry of 1. 1 plus 0 is 1. 1 plus 1 is 0, and we have a carry of 1. 1 plus 0 is 1. 1 plus 1 is 0, and we have a carry of 1. 1 plus 1 is 0, and we have a carry of 1. So the carry flag should be 1, and that's right. Let's look at the result. The result is all 0, so the 0 flag should be 1. That's right. The 8 bits is 0, so the sign flag should be 0. And finally, the parity, the number of ones here is 0. 0 is considered an even number. So the parity flag should be 1. Okay. That's good. Now, how to deal with 16 bits? So in the examples, the two examples that we see, it was 8-bit. What is the difference if we do 16-bit? So there are two differences. First, the sign flag and the carry flag as well. We'll look at D15, not bit 7 or bit number 7. So we look at, for the carry, we look at the bit number 15 if there is a carry from this operation or not. And the parity all the time look at the lower order byte or 8 bits. So although we have 16, we're gonna count the number of ones only in the lowest or least significant 8 bits. For example, if the result is like this. This is 16-bit, right? This is 16-bit. What is the parity here? So if this is a result of some kind of addition, for example, what would be the parity flag? So we're gonna look at the 8-bit, the least significant 8-bit, which is those guys. If we count the number of ones here, it's 1. This is an odd number, so the parity flag here should be 0. If you look at the 16, that's wrong, because if you look at the 16, the number of ones is 2. That means the parity flag will be 1, because this is an even number, and that's wrong. You should look only at the least significant 8-bit. That's very important. Let's see an example here with 16-bit operation, and of course here we are using AX because AX is 16-bit. So we're gonna add 3, 4, 5, F5 and 9, 5 EB. And this is, let's do the operation. 1 plus 1 is 0, and we have 1. 1 plus 0 is 1. 1 plus 1 is 0, and we have 1. 1 plus 1, we have 0, and we have a carry of 1. 1 plus 1, we have 0, and we have a carry. And again, before you continue, the auxiliary flag should be 1. Let's check. Yes, that's right. 1 plus 1, 0, and we have a carry of 1. 1 plus 1 plus 1 is 3. 1, we have a carry of 1. 3 again, 1, we have a carry of 1. 1 plus 1 plus 1, 1, and we have a carry of 1. 1 plus 1 is 0, and we have a carry of 1. 1 plus 0 is 1. 1 plus 1 is 0, and we have a carry of 1. 1 plus 0 is 1. 1 plus 1 is 0, and we have a carry of 1. 1 plus 1 is 0, and we have a carry of 1. 1 plus 0 is 1. 0 plus 1 is 1. So the carry, since there is no carry from the operation number 16 here, this operation here, then the carry is 0. Also, if this is an 8-bit operation, you see here the operation from a bit number 7 or the 8th operation has a carry, but we are not looking here at the 8-bit operation. We are looking here at 16-bit operation. So the carry flag is 0. Let's check the parity. So the parity, we're gonna look at the least significant 8 bits, and we have here 3 ones. This is an odd number, so the parity should be 0. That's right. That's not 0, so the 0 flag should be 0. That's right. The sign here is a sign of bit number 16, and it's 1. Okay. Let's take another example. We're going to add here 4 A's and 5, 5, 5, 6. So 0 plus 0 is 0. 1 plus 1 is 0, and we have a carry of 1. 1 plus 1 is 0, and we have a carry of 1. 1 plus 1 is 0, and we have a carry of 1. Before you continue, the auxiliary flag is 1. And that's right. 1 plus 1 is 0, and we have a carry of 1. 1 plus 1 is 0, and we have a carry of 1. 1 plus 1 is 0, and we have a carry of 1. 1 plus 1 is 0, and we have a carry of 1. 1 plus 1 is 0, and we have a carry of 1. 1 plus 1 is 0, and we have a carry of 1. 1 plus 1 is 0 again, and we have a carry of 1. 1 plus 1 is 0, and we have a carry of 1. Wow. 1 plus 1 is 0, and we have a carry of 1. 1 plus 1 is 0, and we have a carry of 1. 1 plus 1 is 0, and we have a carry of 1. 1 plus 1 is 0, and we have a carry of 1. So the operation number 16 here result in a carry. So the carry flag should be 1. This is a 0. This is 0. So the 0 flag should be 1. That's right. The sign here, look at the bit number 15 or the 16th bit. It's 0. So the sign flag should be 0. The parity, look at the first 8 bits. The number of ones is 0. That's an even number for some reason. So the parity should be 1. Okay. One important observation here is that the move or data transfer instructions does not change the flag. So the flag, it changes usually with arithmetic operations, like the ones that we see. So this instruction will not change the flag. This instruction will not change the flag. This instruction as well. This instruction as well. Only the one that changes the flag register is that one. Add AX and BX. So let's add AX and BX. AX is 94C2. This is 94C2. BX is 323E. 323E. So let's add them together and check. So 0 plus 0 is 0, and we don't have a carry. 1 plus 1 is 0, and we have 1 a carry. 1 plus 1 is 0, and we have 1 as a carry. 1 plus 1 is 0, and we have 1. Auxiliary flag is 1. That's right. 1 plus 1 is 0, and we have a carry of 1. 1 plus 1 is 0, and we have a carry of 1. 1 plus 1 is 0, and we have a carry of 1. 1 plus 1 is 0, and we have a carry of 1. 1 plus 0 is 1. 0 plus 1 is 1. 1 plus 0 is 1. 0 plus 0 is 0. 1 plus 1 is 0, and we have a carry of 1. 1 plus 1 is 0, and we have a carry of 1. 1 plus 0 is 1. 1 plus 0 is 1. So there is no carry from the 16th operation. So the carry should be 0. That's right. The sign is 1. That's right. This is not 0. So 0 flag should be 0. That's right. The parity. Wow. So the parity, if we look at the 8 bits here, this is 0 number of ones, 0 ones. That's an even number. So the parity flag should be 1. That's right. If you look at the 16 bit as a whole, the number of ones is 5. And this will make the parity flag 0, but this is wrong because we are looking only at the least significant 8 bits. Now, when to use the 0 flag? The 0 flag is really important because we use it to make loops. So in assembly language, we can do loops as well. Okay. One thing you should know about assembly language is that whenever you do, for example, C++, C++ does not transfer directly. The compiler, which translates C++ to machine language, does not transfer it to machine language directly. No. It transfers it first to assembly, and from assembly, the assembly is decoded or transferred or translated into machine. So you have all the time a middle ground between the high-level language and the machine language or zeros and ones, which is the assembly language. So any language is translated into assembly first, then from assembly to machine language. Okay, so since we have looping in any machine in any programming language, then in assembly we should have loops as well. Okay, loops is a future near future lesson, but we're gonna highlight here an example. Okay, and we're gonna explain. It's really self-explainable, but I'm gonna explain it again. But don't worry if you didn't understand it very well. So the 0 flag, as I said, is used in looping, and we mark, if you have a loop, for example, like for I equal to 0, I less than 4, I plus plus, something like this. Okay, so you are counting here from 0 1, 2, 3, 4, which is 5 times. So you are looping or 5 times for this loop. So what we're gonna do here, if you wanna repeat something 5 times, you do this trick here. First, you put 5 in a register like CX. So CX now has 5. Then you for example, put some value in BX. This I'm gonna explain the code, and once I explain it one by one, you're gonna understand how we can make loops in assembly. Also, again, this is a future lesson. So I'm gonna put in BX here 200 hexadecimal. Remember, CX here has a 5. It's 5 here. Hexadecimal is just like 5, decimal. And AL has 0 initially. Then add LB here. This is label. So this is label for the line. It's not a code. It's just a name for this line. So that's basically the loop body, as we will see now. That is the instructions that will be repeated. So let's check. Add AL and BX. BX between these brackets means memory location. So this means go to memory address BX, and bring what's in there and add it to AL, I'm sorry. So let's assume this is the memory. The memory is just locations like this. Okay. And here is the location number BX. It's an address. And this location, for example, has 1. Okay. Good. So in the beginning, I'm going to bring this 1 and add it to AL. So AL now will become 1. Increment BX. So BX will be 201 hexadecimal. Increment means increment, add 1. Decrement CX, so CX will be 4. Then the key command here, instruction. Jump if not 0. So what the assembler will do here, jump not 0 means it checks the 0 flag. If it's not 0, go to add LB. Otherwise, continue in the program. So if there is something written here, another instruction, it will go and execute this instruction. So when we decrement CX become 4. Okay, that's not 0. So the 0 flag will be 0. So let's add the 0 flag here. The 0 flag after decrementing CX, the 0 flag will be 0 because this is not 0 result. Okay, we're gonna come here again. So we're gonna jump to add LB, add AL and BX. Now BX is looking for, so this is previously 200H, for example. This is 201. Let's assume also there is a 1 here. So I'm gonna add to L another 1, so it become 2. Increment BX, so BX will be 202 hexadecimal. Decrement CX, so this will be 3, and this is not 0, so the 0 flag will stay 0. Jump not 0, no, it's not 0. Yes, it's not 0, so we're gonna jump. Add L and BX. BX now is 202, so it's looking to another location. Let's assume another 1 here. So I'm gonna bring 1 and add to AL, increment add, so this will be 3. Increment BX, so BX will be 203 hexadecimal. Decrement CX, so CX will be 2. Again, the 0 flag will not change because CX, the last operation, doesn't result in a 0. Jump not 0, so I'm gonna jump because it's not 0. The 0 flag is 0. Add AL and BX, so this will be 4. Okay, increment B, so 204. So this is 203. This is 203. This is 204. Again, it has 1. This is just an assumption. Add again, so this will become 5. Then decrement CX, so the CX will be 1. 0 flag is still 0. I'm gonna jump again, add AL and BX. So again in 204 there is a 1. So add to AL will be 6. Increment BX, so BX will be 205. Now decrement CX, 1 minus 1 is 0. So the 0 flag will be 1. Jump not 0, it's a 0 now. So it will not jump. So it will continue and execute the next instruction. If you didn't understand this, program very well, you can, of course, repeat the recording. But again, if you didn't even understand from repeating the recording, or watching it again, don't worry, because we're gonna, take looping in details in the future. Okay, guys, that was it for the flag register. Thank you very much, and see you in next videos. Bye-bye.